Alright, in this explainer, we are going to deconstruct a classic GCSE geometry proof. And I'm not just going to show you how to get the right answer, we're going to look at how to think like an examiner, using the official mark scheme as our guide to lock in every single one of those precious marks. So, how do you get full marks on one of these? This is the kind of question that really separates the top grades from everyone else. It's not just about crunching the numbers. It's about presenting a totally bulletproof argument. We're going to decode that exact process using a real question from an exam. Okay, let's get stuck in. We are tackling a quadrilateral problem taken straight from a recent GCSE paper, and we're going to solve it together step by step. So here it is, our challenge. We've got this quadrilateral, ABCD, and as you can see, its angles are given as these algebraic expressions. Our mission? We have to prove that this shape is a trapezium. And that word prove is so important. It means we need a rock-solid, logical argument with super clear working, not just a final number. Okay, so before we can prove it's a trapezium, we've got to be crystal clear on what a trapezium actually is. Simple enough. It's a four-sided shape that has at least one pair of parallel sides. So that's our goal. We just need to prove that one pair of those sides are parallel. But how do we actually do that? Well, in geometry, the secret to proving lines are parallel is all about the angle relationships. We're hunting for something called co-interior angles. Now, these are the angles that are on the same side of a line that cuts across two others. A good way to remember it is to think of them forming a C or a U shape. If we can show that a pair of these angles add up to exactly 180 degrees, then bam, we've proven the lines are parallel. That's our game plan. All right, let's get started. The first big step in a lot of these geometry proofs is turning the picture into the language of algebra. It's time to build our equation. So, what's the one golden rule we know about any four-sided shape, no matter what it looks like? That's right. The angles inside it always add up to 360 degrees. This is the key bit of geometry that's going to let us build our equation and crack this thing open. And this is how we do it. We literally just take the four expressions for the angles, add them all together, and set them equal to that magic number, 360. Just writing this down, this full equation, is what the examiner is looking for. That right there gets you your first mark, because it shows you know the fundamental rule. Now here's something interesting. The mark scheme actually shows there's another way you could have started. You could have assumed a pair of sides were parallel right from the beginning, and then tested if that was true. For example, you could say, okay, let's pretend the top and bottom are parallel, which would mean angles B and C have to add up to 180. You could set up that equation and solve it. But we're sticking with the 360-degree method because it's a bit more thorough. It doesn't make any assumptions up front. Okay, equation set. Now for the fun part, the algebraic heavy lifting. Let's solve this thing for x. Let's just walk through this nice and steady. First, let's scoop up all the x terms. We've got a 3x, a 4x, a 2x, and another 4x. Add all those up and you get 13x. Easy. Next, the numbers. We have a -3, plus 15, plus another 15, and plus 8, which all comes to 35. So our big, messy equation just became 13x plus 35 equals 360. Much better. To get x on its own, we'll subtract 35 from both sides, which leaves us with 13x equals 325. And the final step? Divide 325 by 13, which gives us x equals 25. Boom! This is a massive step forward. The mark scheme gives a really important accuracy mark for getting this value right. So this is a huge milestone. So we have x. But hold on, we're not done yet. We haven't actually proven anything about the shape itself. Finding x is just part of the puzzle. The next logical step is to use this value to find out how big each angle actually is. So we just plug x equals 25 back into each of those original expressions. For angle A, we get 72 degrees. For angle B, that's 115 degrees. Angle C works out to be 65 degrees. And finally, angle D is 108 degrees. Now let's do a quick sanity check. Let's add them up. 72 plus 115 plus 65 plus 108, and yep, it equals 360. Perfect. That gives us a lot of confidence that our value for x was spot on. This brings us to the home stretch, the final crucial step. This is where we connect all our calculations back to the original problem and lock in those final marks for the proof. Remember our mission? We needed to find a pair of co-interior angles that add up to 180. Well, let's test out angles B and C. We've got 115 degrees plus 65 degrees, which equals exactly 180. There it is. This is the golden ticket.
the key piece of evidence we need to finish this.
So how do you actually write this down for the examiner? This part is so important. You have to be precise. You must clearly state the geometric reason for your conclusion. A perfect sentence would be something like, since the co-interior angles B and C add up to 180 degrees, the sides AB and DC must be parallel. Therefore, the quadrilateral ABCD is a trapezium. That clear, logical chain of thought, that's what gets you the full marks.
And there you have it, a full mark proof from start to finish. It's a really powerful process, isn't it? You use a geometry rule to build an equation, you solve the algebra, and then you use that result to prove something about the shape. So I'll leave you with a question to think about. What other shapes, maybe like a parallelogram or a kite, could you prove things about using this exact same method? Give it some thought. Thanks for joining me.